Okay, today we're going to take a look at continuity with limits. So let's go ahead and start. Learning goal. Students will be able to understand when a function is continuous. So we've looked at this in previous videos, but we're going to do it once more analytically. Let's go ahead and review. Definition of continuity. So very important that you know these three things. Continuity at a point. A function f is continuous at c, which is on the x-axis, if the following three conditions are met. Now the first one, f of c is defined. What this means is that you have a height everywhere on your function. Number two, the general limit exists. So basically the limit from the left and the right have the same height. And then number three, you have a limit as x approaches c of f of x, and you have a height everywhere that fills in any holes that you might have. So here's a graph, for instance, and it's nice and continuous. And I know because I haven't had to pick up my highlighter once. And if you're wondering about number three, basically what had happened is this. I had a hole and it looks like f of c fills that hole. So it still makes it continuous. Okay, so let's take a look at the first example. It says, does the limit as x approaches 2 of f of x exist? And if it does, is it continuous? Now what I want you to fix on this little worksheet is this. This is just going to be positive 2. This is going to be positive 2. And this will be positive 2. Okay, so let's go ahead and see if number 1 is true or not. F of x is defined. Now it is because you can tell right here that our domain is equal to. So if I don't have either one equal to, then it wouldn't be continuous and you could stop right there. It wouldn't help you with the limit, but it would help you with continuity. So this one is yes. Okay, we're in good shape. Now we want to show that, let's say number 3, okay, if the left and the right are actually equal to each other. First you have to figure out which one's the left and which one's the right. To do that, you simply look at the inequalities. Because this says less than, that means left. Because this says greater than or equal to, well, just the greater than, this means right hand side. So basically the domain here is all the stuff on the left, so that would be left hand limit. Domain here is everything on the right. So let me go ahead and sketch that out, or actually write that out. Limit as x approaches 2 from the left. Now once again, we know this is left, so this is the left hand function. Negative 2x plus 6. To prove that the general limit exists, both these heights have to be equal. Let me plug in a 2 and see what happens. You get negative 2 times 2 plus 6. That makes negative 4 plus 6, which makes 2. Okay, so the right-handed limit as x approaches 2 from the right. Now that's this function, x squared minus 1. If I plug in, I get 4 minus 1, which in this case makes 3. So unfortunately here, our general limit does not exist, so that's no. So therefore, this would not be continuous at x equals 2. Is the function continuous? Well, in this case, I've got either a jump discontinuity, so I would say no on this one, and definitely no on being continuous. Alright, so let's take a look at example B. These are a little simpler. It basically says for what value of a is the function continuous. Now remember, I'm still using all three properties, or parts of the definition. So in the past I just kind of set these up and made them equal and then plugged in the domain, but you'll see here why I really should have proper notation, and I should say that the left hand side, which is this because it's less than, so left, is equal to the right hand side if they're continuous, that is. So let me go ahead and erase the limit and write a little higher up. Grab Mr. Blue for this one. So limit as x approaches 0, and I know it's 0 because that's the domain, from the right. The right hand side would be this one right here, a minus 2x is equal to the limit as x approaches 0 from the left, which is 4 sine x over x. Now the beautiful thing is we have a property. We have a property, if you recall, it says limit as x approaches 0 of sine x over x. That's equal to 1. So on this side right here, I simply have 4 times 1. On the left side, you just evaluate. You get a minus 2 times 0. Now if you're like, why aren't you evaluating the a? Well, x approaches 0, so that's what I'm evaluating, the x value. So you get a is equal to 4, and you're done. So basically, if you want this function to be continuous, g of x, you'd have to put a 4 in for a. Alright, looking great. You try. This is where I'm quiet for a couple of minutes and you actually get to pause the video. If you just want to watch me work it out, that's fine, but I'll give you a moment, so give it a try. Okay, let's see how you did. Let me grab Mr. Green here. So it says find the limit. It's not asking me about continuity, just find the limit as x approaches 1 of f of x. Okay, so now to define some stuff for you, because these are not inequalities, this, my friends, is just the order pair 1, 3. And remember, limits don't care about order pairs, so I don't have to worry about that. Now, if I'm just strictly finding the limit, the general limit, I can just use the function. So the function is x squared plus 5. If I evaluate, I get 1 squared plus 5, which makes 6. So the general limit is equal to 6. I hope you didn't make too much more of this problem. It wasn't that crazy. I wasn't meant to trick you. It was just showing you some application. You really have to know in your piecewise function which ones are order pairs and which ones are functions and lines and things of that nature. So let's go back up to our learning goals. Students will be able to understand when a function is continuous. It's all about these 3 little parts of the definition. The height has to exist, the general limit has to exist, and then if you do have a hole, that it's filled in. Alrighty, I'll see you in the next video. Thank you.